In a PNP transistor, there are two junctions. One junction is between the emitter and base, and the other junction between the collector and base. The base region, that is, the N region between the two junctions, is connected to the base terminal. And between these 2 points exists the inherent resistance of the N-type material. A junction can be biased in either the forward direction or in the reverse direction. First, let us consider the situation when no voltages are applied to the two junctions. In this case, the majority and minority concentrations, shown on a logarithmic scale, are at their respective equilibrium levels. Thus, no current flows through the transistor. This is clearly illustrated by the horizontal positions of the minority concentration graphs, which are drawn here on a linear scale. We will now apply a reverse voltage to both junctions. The result will be an increase in the widths of the two barriers, which has the effect of allowing only minority charge carriers to flow across the barriers. The minority concentrations will therefore decrease in the vicinity of the barriers, and as the base region is so narrow, the whole concentration level will be low throughout this region. The concentration curve of the electrons in the emitter forms an angle with a horizontal axis. And the tangent of this angle is proportional to the value of the emitter current. A similar situation occurs at the collector-base junction, which is also biased in the reverse direction. In this case, the concentration curve of the electrons in the collector forms an angle with the horizontal axis, and the tangent of this angle is proportional to the collector current. The emitter and collector currents induced by the applied reverse voltages are very weak. This can also be seen from the equivalent circuit of the transistor, which comprises two reverse biased junctions and a base resistance. Under these conditions, the transistor is said to be operating in the cutoff state. Another state of operation can be obtained by applying a forward voltage to the emitter base junction and a reverse voltage to the collector base junction. This has the effect of reducing the width of the left-hand barrier and enlarging the width of the right-hand barrier. Holes then diffuse from the emitter into the base, flow on to the collector, and are absorbed by it. The minority concentrations will increase at the emitter base junction and decrease at the collector base junction. The concentration curve of the holes in the base forms an angle with a horizontal axis which is large compared with the other angles determined by the electron concentration in emitter and collector. This large angle indicates that a large number of holes flow from the emitter into the base, giving rise to a large emitter current. However, as this small angle shows, there is also a small electron flow in the opposite direction, which adds to the emitter current. The concentration curve of the holes in the base also indicates a large flow of holes into the collector. As we know, these holes originate in the emitter, flow through the base, and are absorbed by the collector, giving rise to a large collector current. In this configuration, the base current is the sum of two small currents. These currents are, firstly, the small electron current flowing in the input circuit, and secondly, a small current which is induced by surface recombination of holes in the base region. In the equivalent DC circuit of the transistor, the forward voltage applied to the emitter base junction corresponds to the large current flowing in the emitter circuit. The reverse voltage, which is applied to the collector base junction, corresponds to a small current flowing in the collector circuit. But we have seen that the collector current is in fact almost as large as the emitter current. Therefore, the equivalent circuit must be modified to conform with this large value of collector current. Only a small part of the collector current will flow in the equivalent circuit shown. The flow of the remaining larger part is represented by shunting the collector base junction with a current generator. The transistor is now said to be operating in its normal state. Another state of operation is obtained by reversing the polarity of both batteries. This, of course, has the effect of reversing the minority concentration graphs. The three currents flowing are directly related to these concentration graphs. The collector current to the electron concentration in the collector and the hole concentration in the base, the emitter current to the hole concentration in the base, and finally the base current to the electron concentration in the collector. However, most of the base current is due to surface recombinations, because here the roles of emitter and collector have been interchanged. We will now develop the equivalent circuit of the transistor for this state of operation. The collector current is very large. The base current, although smaller than the collector current, is, due to the many surface recombinations, larger than with a transistor operating in the normal state. The reverse bias applied to the emitter-base junction is not consistent with a comparatively large emitter current flowing. Therefore, in the equivalent circuit, this flow will be represented by shunting the junction with a current generator. The transistor is now said to be operating in the reverse state. The final state to be examined is achieved by reversing the polarity of the battery in the emitter-base circuit only. When both circuits are interrupted, the barriers assume a width corresponding to the equilibrium condition, and the minority concentration graphs become horizontal. If the circuits are again closed, both junctions will be forward biased. The widths of the barriers will decrease, and holes will diffuse from both the emitter and the collector into the base. At the same time, electrons will diffuse from the base into the emitter and the collector. Consequently, the concentration of holes in the base will increase considerably. And the electron concentrations in the emitter and the collector will, near the barriers, also increase. When the values of the two voltages applied are almost the same, the concentration graph of the holes in the base will be almost horizontal. Only a proportion of the current flowing in the emitter circuit corresponds to the angle formed by the concentration graph of the electrons in the emitter. The rest is due to surface recombinations. Similarly, only a proportion of the collector current corresponds to the angle formed by the concentration graph of the electrons in the collector. Here again, the rest is due to surface recombinations. Both collector and emitter currents are in this case rather weak. But if we now increase the value of the forward voltage applied to the emitter-base junction, the number of holes diffusing from the emitter into the base will increase considerably, and most of these holes will be absorbed by the collector. The large angle now formed by the concentration graph of the holes in the base indicates that the emitter and collector currents flowing are also large. However, the collector current is now flowing in the opposite direction. The equivalent DC circuit will be developed in two stages. Firstly, the forward voltage applied to the emitter-base junction requires that a current generator be placed across the collector-base junction. And secondly, the forward voltage applied to the collector-base junction requires that another current generator be placed across the emitter-base junction. The transistor is now said to be operating in the saturation state.